So now let's hit vectors. So quick review of vectors before we talk about derivatives with vectors. Vectors give both a magnitude and a direction. So velocity is a nice example of a vector because there's both magnitude and direction, meaning a size and what way we're going. Because it is a magnitude and direction, you see vectors a ton with motion. And then just as a reminder, when you hear me use the word scalar, that is a number with no direction. So it's kind of, vectors have a number with a direction. Scalars are just the number, no direction. So scalars are not vectors. In AP, we're going to be using component form for vectors, which looks a little bit like an ordered pair, but instead of parentheses, we have these like pointy parentheses. I'm sure there's a name for them. I just don't know what the name is. It has been suggested in the past by other students that I should call them pointices instead of parentheses. And I see no reason why we can't just make up the word pointices. Where the x-coordinate is not giving me where to graph it, it's telling me what direction to move left or right and how far from where I started. And y is doing the same but vertically. So when I see the vector -3, 2, it means I'm moving left 3 and up 2 from wherever our current position is. We are able to do vector operations. And this is one of the reasons we use component form, is the operations are much easier in component form. I can add and subtract vectors in component form by just add and subtracting their components. So if I have the vector 2, 7 plus the vector 8, 12 minus the vector -3, 1, I would just go ahead and combine, all of the x-coordinates together. So 2 plus 8 minus a -3 would be 13. And then 7 plus 12 minus 1 is 18. And that is our vector that we get after all the adding and subtracting. Scalar multiplying is taking a scalar times a vector, and this is like doing the distributive property. I'm just going to take and multiply each part, each component, by that scalar. So now I had said that motion is very, very common with vectors, typically based off of what we call a position vector, which is just saying this is where it is moving. It's like displacement, but for various reasons, it's called a position vector and not a displacement vector. The velocity vector, we just take the derivative of the x component and we take the derivative of the y component of the position vector, because velocity is the rate of change of our displacement. Speed is the magnitude of the velocity. In one variable scenarios that we're used to with, in other words, motion on one line, like left and right or up and down or forward and backward, we always just say, well, that's the absolute value of velocity. But if we think about what absolute value really is, that's really the magnitude. You take away the direction. In other words, you're not worrying, is it positive or negative? You're just saying, what's the distance? So since we're now moving in two different directions at the same time, not just left and right, but left and right and up and down, when we talk about the size, the magnitude of velocity, we have to approach it a little differently. And in vectors, it's not called absolute value, it's called the norm. So the norm of velocity is what speed is. And we find that by doing the Pythagorean theorem on the velocity vector, because that will give us how long the velocity vector is, its magnitude. And then the acceleration vector is the derivative of the velocity vector, which means it's the second derivative of our position vector. So we're just finding the second derivative of the x component of the position vector and the derivative of the y component of the position vector. These are generally pretty straightforward. The notation just makes it look scary. So here I have a particle that's moving with a position vector, sine 4t and t cosine 2t. And I want to find the velocity and acceleration vectors, and then find the velocity, acceleration, and speed when t is equal to pi over 6. So if I want to find the velocity vector, I'm going to need to take the derivative of the x component of my position vector. And so I've got the cosine of 4t, but then chain rule times the derivative of 4t. And t times cosine of 2t is going to require the product rule. So I have first times the derivative of the second, but I need the chain rule on that derivative of the second, plus second times the derivative of t, which is 1. And I'm going to clean that up a little bit because I know I'm going to have to take the derivative of that for the acceleration vector. So this is 4 cosine 4t and negative 2t sine of 2t plus cosine of 2t. And now I can take the derivative of that to get the acceleration vector. The 4 is a constant multiple times the derivative of cosine, which is negative sine. Inside stays the same, but then times the derivative of the inside because of chain rule. For negative 2t sine of 2t, that's a product, so I have to do the product rule. So I have first times the derivative of the second times the derivative of 2t because of the chain rule, plus sine of 2t times the derivative of negative 2t. And then I have to finish the rest of my derivative there. So derivative of plus cosine 2t is going to be minus sine of 2t times the derivative of the 2t. And that's ugly, but that is my acceleration vector. I can choose to clean that up a bit if I want. I am not choosing to. But then I need to use these to actually do this when t is pi over 6. So I'm going to start with the velocity at pi over 6. Well, my velocity is going to be 4 times the cosine of 4t, and t is pi over 6. So I have 4 times the cosine of 2 pi over 3. And then I'm going to have negative 2 times pi over 6, which is negative pi over 3, times the sine of 2 times pi over 6, which is pi over 3, plus the cosine of pi over 3. And evaluating that, cosine of 2 pi over 3 is going to be negative 1/2. Then I have negative pi over 3. The sine of pi over 3 is rad 3 over 2. And the cosine of pi over 3 is a positive 1/2. And there is my velocity vector. Again, I can clean that up a little bit. So that's going to be negative 2, and then negative pi rad 3 plus 3 all over 6. I chose to make it all one fraction, but that's not a requirement there. For then the acceleration vector, I'd have 4, then the negative sine of 4 pi over 6 is sine of 2 pi over 3, which would be rad 3 over 2 times 4. Then that's my x-coordinate. Then for my y-coordinate, I have negative 2 times pi over 6, which is negative pi over 3. Then I have the cosine of pi over 3, which is 1/2. Then I have the 2 plus sine of pi over 3 is rad 3 over 2 times the negative 2 minus sine of pi over 3 times 2. And there's my acceleration vector. Aren't you glad we're not required to simplify? And then finally, for speed, at t equals pi over 6, I am going to do the Pythagorean theorem on my velocity. So I have the square root of the x component squared plus the y component squared. And I am not going to simplify that. That is my speed.